Hello, in this video we're going to write out all of the resonance structures for nitric acid. First we need the Lewis dot structure, so we will have to write out all the different types of atoms we have. We have hydrogen, nitrogen, and oxygen. Hydrogen's configuration is 1s1. Nitrogen has a helium core, 2s2. 2p3. Oxygen has a helium core, 2s2, 2p4. This gives us 1 valence electron, 5 valence electrons, and 6 valence electrons. If we get our bank, we have 1 hydrogen giving us 1 electron, plus 1 nitrogen giving us 5 electrons, plus 3 oxygens giving us 6 electrons, for a total of 24 electrons. Now we need to place the less electronegative atom in the center. That would be hydrogen, but we know hydrogen can't be in the center, and we're being given a little hint here. We know hydrogen is going to be bound to an oxygen, and then so nitrogen is going to be bound to an OH and 2 oxygen atoms. If we interpret all of that together, I'm thinking nitrogen needs to be in the center. We'll have an oxygen, and that OH. I had 24 electrons to work with. I just made 1, 2, 3, 4 bonds. 2 electrons for each one of those bonds. 24 minus 8 is 16 electrons left over. And now we can start to fill in our octets. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That exhausts our bank, so let's take a look at our octets here. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8. He's happy. This guy looks the same. He's happy. This guy, 1, 2, 3, 4, 5, 6, 7, 8. Still happy. Hydrogen, 1, 2. That's all hydrogen wants. He's happy. Nitrogen, 1, 2, 3, 4, 5, 6. He's not happy. He needs somebody to share electrons with him. Now, the question becomes, who's going to share those electrons? We have 2 equally likely choices here, and then we have this guy that's a little bit different. So let's consider the 3 cases that we have here for a moment. Let's see if we can use formal charge to figure out which of these is correct. So we're going to start with the valence for each one. 6, 6, 6 for all of the oxygens. That is their valence number. We're going to give a 5 to all of the nitrogens. And we're going to give a 1 to all of the hydrogens. And then we're going to subtract our count. Now our count's different. We're going to give a 1 to each one of the dots and a 1 to each one of the bonds, not 2 to the bonds like we do for the octet. So 1, 2, 3, 4, 5, 6, minus 6, 1, 2, 3, 4, 5, 6, 7, minus 7, 1, 2, 3, 4, minus 4, 1, 2, 3, 4, 5, 6, minus 6, 1, minus 1. Okay, now we can come over here. We're going to get the same kind of results. For this guy, we're just going to switch these two. Now over here, all of these, this one's going to be minus 7, minus 7, minus 4, minus 1, 2, 3, 4, 5, minus 1. So altogether we get a 1 minus here, 0, 1 plus, 0, 0, 1 minus, 1 plus, 0, 0, 0, 1 minus, 1 minus, 1 plus, 1 plus, and 0. So we can see that over here, no matter what, we're going to wind up with some formal charge. But in these two cases, the two on the left here, we have a 1 plus and a 1 minus. In this case, we've introduced a 1 minus, a 1 minus, a 1 plus, and a 1 plus. We've introduced more formal charge than is necessary. For that reason, this guy is not a valid structure, and we're going to expect that these two that are equally likely because they have the same number of formal charges and there's no structural difference between which oxygen we chose are going to move back and forth. These two are going to be our resonance structures, meaning that we can write a resonance hybrid that's going to look like this. And then we can write out these two lone pairs because they do not change between the two structures.